Apparent weight is a tricky concept, so I'm going to do one more example just to talk you through it. Basically, what apparent weight is if you take a solid a solid that's going to sink in water. Once it's in water, here, let's do a little picture. Once it's in the water, we still have gravity pulling down on it. And kind of in a funny notation, gravity is really what we use in everyday life when we say weight. So we've still got gravity pulling down on this thing, but this buoyancy force adds an upward force to it. The buoyancy force upward is the weight of the displaced water. So really, in an apparent weight question, we need to find two things: the weight of the actual object, which is just the force of gravity on the object, and then the weight of the displaced water, which is going to be the force of gravity on the equivalent volume of water. So a buoyancy force question, we're going to need masses. To get masses, we're going to use density, so that means we're going to need volume. This one I made up a cube, but it could be any shape. Volume is always, volume of a cube is just multiply it out, 10 times 10 times 10. The first issue is it's easier to convert these to meters first. So make this 0.1 meter times 0.1 meter times 0.1 meter. Otherwise, you might goof up and think that to go from centimeters cubed to meters cubed, you just move the decimal 2 places. But basically, each of those lengths, you move the decimal 2 places, so you end up moving the decimal place like 6 places. So just I've learned it's a little bit easier to convert those to meters first. When we do that, we get a volume of 0.001. I'm going to start with the chunk of metal. The numbers I made up in the question, we know that the density of the metal is 5,000. And the connection is mass is equal to density multiplied by volume. So the mass of our chunk of metal is the 5,000 that was given, multiplied by the volume that we calculated. And I made the numbers a little mental math or calculator time. I tried to make the numbers not terrible. Basically, that works out to be exactly 5 kilograms. That's the mass of the piece of metal. For buoyancy, for apparent weight stuff, we need the weight. Weight, physics people don't really love the word weight, but weight just basically means the force of gravity, which means we're going to take the number in kilograms and multiply by our 9.81 number. Oops, come back. 5 times 9.81. That works out to be 49.05. The 49.5 number, that's the weight of the water. If we go back to our free body diagram, that's this downward arrow. We've got a 5 kilogram block of metal. Gravity's pulling it down at 49.05. If it wasn't in the water, that's how much force you'd have to put on it to lift it. The buoyancy part, because it is in the water, now we have to switch to thinking about water. You don't have to memorize it. The density of water is 1,000. The buoyancy force is related to the weight of the displaced water. So to get the weight of the displaced water, we need to know the mass of the displaced water. So we take our 1,000 for the density, multiplied by the volume that we calculated. When we dunk that block, that cube of metal in the water, it's going to displace its own volume in water. So we use that same volume number. Again, tried to make kind of easy numbers to work. This works out to be exactly 1 kilogram. That tells us the mass of the water that's displaced, the weight of the water that's displaced. We don't really like the word weight in physics, but it's mass times 9.81. In this case, it's 1 times 9.81. So the weight of the displaced water is 9.81 newtons. This one over here is the water. This one over here is the weight of the metal. Now think back to our free body diagram. The 49 number is what's pulling this thing down into Earth. And because of this fluid situation, the pressure of the water pushes back up on it, a smaller force, a 9.81. So to finish off apparent weight, our last step is the apparent weight is the difference between these two. We've got a tug of war, 49 pulling it down, 9.8 pulling it up. Apparent weight is just what we have left over when we add those vectors. So in this case, the winning force is our 49.05, and the buoyancy force, 9.81, gives us a number of 39.24. That is the apparent weight of the metal. If we dump that 10 by 10 by 10 cube of metal into water, instead of taking a force of 49 to beat gravity and lift it, it would only take a force of 39.24 to beat gravity and lift it. That water added a little bit, made it a little bit easier to lift. That is a classic apparent weight question.